Justin Robinson here is a lecturer at Georgia State University in the Department of Physics and Astronomy. He is also the director of outreach for our Department of Physics and Astronomy. He started this chapter of Astronomy on Tap here in Atlanta and has seen it grow to several different branches. Sometimes we talk here, sometimes we talk at the Imaginarium location. And
the Ponce Brew Terminal.
The Ponce Brew Terminal is up and coming. Dr. Justin Robinson here received his PhD from Georgia State University as well in 2022 under the advisement of the Dr. Misty Benz. And not only does Justin take care of all of our scientific astronomy outreach in the department here at Georgia State, he also teaches students at Georgia State University, does his own research, and advises undergraduate researchers in their quest for obtaining a degree in physics or astronomy. Today, Justin is here to talk to you all about dark matter, so let's give it up for Dr. Justin Robinson!
Good evening, everyone, and welcome to Astronomy on Tap Atlanta. It feels so good saying that when I am the speaker. It's been a while since I've been in front of you actually giving the talk. It feels so good. So, thank you, everybody, for bearing the storm to be here. And I promise we will be turning on the World Cup after I finish. So please enjoy your beer and buy more by the time that I am done. So I came back to talk to you today because there have been very, very, very interesting developments in the research area of dark matter. So I figured I'd give you the rundown of why dark matter, what dark matter, who dark matter, and go from there. Our story starts with gravity, and the huge assumption is that we think that we completely understand how gravity works. So this lovely animation shows you the different rotational velocities of the planets of the solar system. Mercury makes a lap around the sun faster than any other planet because Mercury is closest to the sun. Therefore, Mercury feels the strongest gravitational force from the sun, meaning it's being pulled more than any other planet, which means it's going to move faster around the sun. Not only does it move faster around the sun, it has to complete a smaller lap around the sun compared to any other planet, and so it completes more laps around the sun faster than anybody else does. And then Venus is in second place, and we're in third place, and Mars is in fourth place, and so on and so on and so on. If we were to analyze how fast each planet is going around the sun as a function of how far they are away from the sun, or in other words, if we study the rotation curve of the solar system, where on the y-axis here is how fast everybody is traveling, Mercury is traveling the fastest, and on the x-axis is how far each planet is away from the sun. You'll notice that as you increase in distance away from the sun, as you increase in your x-axis, the orbital speed decreases on the y-axis. Everybody gets slower the farther they are from the solar system. And so we're like, gravity. That's it. That's all she wrote. That's awesome. And so we expected that same sort of phenomenon for every single system that had things orbiting around a common center of mass or common center of gravity. The sun has by far the most amount of mass in the solar system. In fact, it makes up 99.8% of the mass of the solar system. Jupiter makes up 0.19% of the mass of the solar system. And the other 0.01% is everybody here and everything else. So if any system that we observe has things going around it due to gravity, then we expected nothing other than this. There's going to be systems with more mass, there's going to be some systems with less mass, there's going to be some systems with lots of things orbiting around them, some systems with not a lot of things orbiting around them, but why would it be different? Because everything that's orbiting in a circle in these systems is due to the force of gravity. So when we looked at other galaxies, like this animation of a spiral galaxy that looks a lot like the Milky Way, we expected the same thing. Where if you'll notice, the stuff that's close to the center is booking it around the center of mass, and then the stuff on the outskirts is still moving in roughly a circle, but it's moving much slower than everything else. That's what we expected. Why would we expect anything different? Introduce Dr. Vera Rubin, a pioneer of galaxy rotation curve studies. I just showed you the rotation curve of the solar system, but you can make a rotation curve of anything if you measure how fast things are rotating as a function of how far they are away from the thing that they are rotating. So in the 70s and in the 80s, Vera Rubin was studying this exact same thing, except for other nearby spirals spiral galaxies that are not of the Milky Way. Here is an example of one of her best results in one of my favorite plots of hers, where you are seeing the exact same thing that I showed you from the solar system. Where on the y-axis we have rotation speed, how fast things are moving, and on the x-axis we have the distance away from the center, or the thing that everything is rotating around. In the solar system, you saw a very steep drop-off. Things that were farther rotated slower. Things that were closer rotated faster. What we see in each one of these, where each of these curves represents a different galaxy, and these curves represent how far we measure things. So these are very small galaxies, these are medium-sized galaxies, these are very large galaxies. You'll see that things speed up, which we expect, and then as you go further and further away from the center, the orbital speeds don't drop off. Everything seems to be maintaining the same speed around the center of a galaxy, even if you get to distances of about 60 kiloparsecs, 60,000 parsecs, that's about 180,000 light years away from the center. So even the stuff on the outskirts of galaxies, which span hundreds of thousands of light years in diameter, you still get things that are orbiting at almost the same speed as the stuff in the center. Oh no. What? Why? What's going on? And that's the same exact question that Dr. Rubin asked. So what we expected to happen was this. Instead we saw, and we still see, this. Where the stuff on the outskirts, this is not, I wish this were a real movie. It's not a real movie, these are animations, but they are based on real data. And these are spiral galaxies that are very, very similar to the Milky Way in size and mass. What we observe for most galaxies that populate the universe, they are not doing what we expected to do when we looked at things in the solar system to compare them. Everything is going like this. It's sort of like, something's wrong. And now we need to explain it, because our model of gravity, which before the 1920s was just Newton's law of gravity. Gravity is a force. Gravity is created by mass. Mass creates an attractive force between other masses, and the more mass you have, or the closer that they are, or both, the stronger that force gets. That is no longer correctly modeling what we see in other galaxies, and the more that we observe these, the more that we saw the same exact thing. So what's our explanation? Well, if mass makes gravity, and if gravity makes things move, and things are still moving very, very fast on the outskirts compared to the inskirts, there just must be more mass there, we just can't see it. Or in other words, we are unable to detect the mass that is required to be here in order for our models of gravity to be correct. They just, whatever it is, if it's there, does not generate electromagnetic radiation. Or it doesn't generate photons. Or it doesn't generate light. All mass, including you all, generate light. I'm not seeing the light that you generate if I'm just looking at you with my naked eye, but if I put on a pair of thermal goggles, I would see all of the light that you are generating right now. All mass generates light. This stuff that needs to be here just doesn't. So what we think is happening is that almost every spiral galaxy in the universe is located in this gigantic cocoon, or what we call a halo of matter, mass, that is generating gravity, that must be there to explain why things are moving as fast as they are on the very outskirts, far away from the matter that we see is there. It just needs to be completely surrounded by this stuff, by these dark matter halos. And so in the 70s, and then moving on to the 80s, we enter this dark matter paradigm, where we start modeling all of these galaxies, assuming they are surrounded by these dark matter halos. And when we input those dark matter halos into our simulations start to create galaxies that look almost exactly like the galaxies that we observe in the universe. So is that the correct solution? It is a solution, and it makes realistic galaxies. And so this has been the case for decades at this point. That is what started our quest to understand what, why, how, where, and when dark matter. Then the Hubble Space Telescope goes up in 1990. And then we had to give it LASIK surgery in the mid-90s, and then in the late 90s, it started taking real pictures. It started seeing these things. These are real images from the Hubble Space Telescope of galaxy clusters, which are represented by these blobs of yellow light, really, really densely packed galaxy clusters. And what you see around them are smeared and magnified and distorted and sometimes duplicated images of background galaxies. If you're savvy, or if you follow astronomy, or if you've been to one of these talks in the almost 3 years that we've been doing this, You might recognize this as gravitational lensing. This can't happen unless Albert Einstein was correct in his description of gravity, otherwise known as the general theory of relativity, where he said, gravity is not a force. You can model it as a force, you can make correct predictions about gravity if you treat it like a force most of the time, but you cannot make correct predictions of all the things that gravity can do unless you treat gravity the way that Einstein saw gravity as, where it's not a force. Space and time are intertwined in a gigantic fabric, like a big piece of rubber, that can be bent and warped and distorted if you start putting mass in it. So if I put a baseball in a big blanket, it makes a little bit of a divot. If I put a bowling ball in a big blanket, it makes an even bigger divot. What does this look like? This grid, let's say, represents space-time. Light travels along space-time like a perfectly paven road. But light can only travel along those roads, it can't deviate. And so if there is a pivot, if there's a dent or if there's a pothole, we all live in Atlanta, so we all recognize how it is driving on potholes. You have no choice. You're not gonna go off of the road just to avoid it. Some of you do, but most people don't. And so your shocks have to deal with the fact that you're driving through a bunch of potholes. Light has the same exact problem. So if we introduce a large concentration of gravity, in other words, mass, any light that is coming from a background galaxy that is trying to get to our observing point travels along these curvatures introduced by large concentrations of mass. And as a result of that, these curvatures of space-time act like a big, thick glass lens, where if I tried to look at one of you through this glass lens, your image would be distorted, it would be magnified, and it would be warped around the edges of this glass. This is a real observation. Hubble has seen this. This can't happen under Newton's description of gravity because there was no warping of space-time. It was just a force. There was no effect on the trajectory that things took through space-time. Einstein changed all of that in the early 1900s. And for the past 100 years, every single thing that we've tried to throw at the theory of relativity to try to prove it wrong has failed. It even predicted correctly what those images of the supermassive black holes that we took in 2019 and 2021 were. If you look at the predictions of general relativity, it's almost a one-to-one match. And the dude wrote that theory down 100 years ago. So if it's wrong, we haven't figured out what to throw at it to make it wrong. It is one of our most robust theories of physics and astronomy that we have, second only to quantum mechanics. So what do we do with this? Well, using general relativity, which is a framework, it says if you put mass in this grid will bend. And if you put more mass in it, the more this grid will bend. And it can predict for you how light travels through these bends in space-time introduced by mass. So we go to this theory, we put it into our very, very sophisticated supercomputers, which Georgia State has a lot of. And we say, all right, theoretically, I have seen this lens. Look at all of these distorted images of galaxies that are in the background caused by the gravity of this foreground galaxy. How much mass would I need to put in an undisturbed cube of space-time in order to create a lens that matches how powerful this lens is? We then compare that to how much mass we can measure by detecting visible light. We say in astronomy, light traces mass. Where there is mass, there is light, because everything that is made of mass is going to emit some kind of light. And we are very good at translating how many photons we detect to how much mass needs to be there. So we say, how much mass needs to be here, period, to reproduce this, because this is exactly what we see. We put that aside. Then we say, how much mass do we actually detect in this region? Let's translate every single one of these photons from all of these foreground galaxies into mass. Then let's compare the two. How much mass is there that we have detected through detecting light compared to how much mass needs to be there to create this lens? And the answer is about 15% on average. So 85 to 90% of the mass that you need to create this effect is not there. Or we can't see it through traditional means of electromagnetic radiation detection. Whatever this is, and it needs to be mass, if Einstein's right, it doesn't emit light. That sucks, because the only things that we have on Earth that we have to understand anything in the universe is detecting light, gravitational waves, or neutrinos. That's about it. That's all we got. We can send satellites out to a couple of different close-by things, but in the large scheme of things, the only tools that we have available to study anything about space is effectively light. We've only detected gravitational waves in the past, 10 years or so, which that won a Nobel Prize. I'm not trying to shirk gravitational wave. It's just, for the longest time of human history, the only tool that we have had to understand how the universe works is by detecting light, and this stuff, if it's there, doesn't. So it's really inconvenient. I love this animation. This is what we observe to be happening everywhere. Everywhere. This is prolific. And it's really because of the Hubble Space Telescope when it went up, because it gave us unprecedented resolution, it gave us unprecedented sensitivity, and we saw these gravitational waves permeating almost every time that we saw a large concentration of galaxies in one place. And every single time that we looked at one of these places and we measured how much mass was there based off of how much light we detect, we always detected a minuscule fraction of the amount of mass that needs to be there to create all of these weird distortions and lensings that you're seeing in this animation. The other poster child for the existence of dark matter is the bullet cluster. The bullet cluster. Which one isn't that pretty? This is a real observation from the Hubble Space Telescope. You've got a very, very nice spiral galaxy over here, and then over here you have a cluster of galaxies. Over here you have a cluster of galaxies. Look at these lensing, distorted galaxies that are here. All this lensing that happens here, and you can see some of the lensing that's happening over here. Luckily enough, you guys, including me, gave NASA $10 billion of all of our taxpayer money to build the James Webb Space Telescope. Yes. James Webb, or J-Dub, or Jimmy, as we call him. Jimmy sees in the infrared, Hubble sees in the optical. James Webb is doing his own thing. It's not a replacement of Hubble. They work together because they see two different regimes of the electromagnetic spectrum. So there have been a lot of follow-up studies of deep imaging made by Hubble, like the one that you're seeing now, and then they look at the same exact field and they see it with James Webb. James Webb has a higher sensitivity than Hubble. James Webb has a larger mirror than Hubble, and it sees a different range of electromagnetic radiation than Hubble. So let's flip back and forth between what Hubble saw and what James Webb saw, and let's see if we can see some differences between the two. Now, look over here, watch. All that squiggle, you don't even see it when it switches back to Hubble. Look at that! And then, that's a lens galaxy right there. And look at all of this lit up mass that you can see with Jimmy. Look at this. All of that stuff right there. And look at the immense amount of lensing that is revealed if you use the higher sensitivity of James Webb. So this is a case study of, if it's not dark matter, then please tell me what the hell is going on. This, yes, you're right. I agree with you. This is a composite image of Hubble Space Telescope deep imaging, J-Dub deep imaging, the Chandra X-ray Observatory imaging. That's with the stuff in, we're just going to call that pink, okay? Maybe magenta, this stuff right here, that stuff right here. The Chandra X-ray Observatory detects X-rays, which are very, very, very high-powered photons that are created by gas that's at extremely high temperatures. Now, usually, you need to compact gas into a very small volume in order to heat it up to the point where it's emitting X-rays. If there are any students that I have in here from this summer, you automatically are annoyed by how many times that I've told you this. If you compress a gas, the temperature goes up and the pressure goes up. So most of the time, you need to have a large amount of mass that is gravitationally compressing a region of gas in order for it to light up this much in X-rays. It is really hard to emit X-rays. The problem with this thing is that the most amount of mass in this cluster is not surrounding the X-rays. The most amount of mass in this region is traced out by this purple stuff. Now, the purple stuff is our estimation of the distribution of dark matter in this region, and it comes from the same process that I told you before. We measured all the light coming from this region, we measured the amount of mass that must be producing that amount of light, we put that number to the side, then we tried to model and reproduce every single lensing signature that we saw here and asked how much mass do we need to reproduce all these lenses. And the difference in the mass needed to the mass observed is what's highlighted in blue. Do you notice the problem? All of the mass is in a different location than all of the gas that needed a lot of mass to gravitationally contract it to heat up to produce the X-rays in the first place. So what the hell is going on? Here's what we think is going on. Here is another optical image of the bullet cluster. Here is an overlay of the X-ray observation. So everything that just lit up was all of the hot gas in that region. Trust me, take my word for it. That's a lot of hot gas. That is a lot of hot gas. And now let's trace out with contours the concentrations of mass that we have not detected electromagnetically, but that must be there in order to produce all of the lensing effects that we observe. Here is one of the most famous dark matter maps available that just got updated in resolution and sensitivity and coverage with Jimmy. Now, what's going on here? Let me rewind this just for a second. Okay. How do we explain this? The model that explains how we get to this kind of object in the first place is you originally had halos of dark matter compressing gas, making it hot, that were gravitationally attracted. The dark matter, if we're right about it, doesn't interact with itself. It doesn't interact with anything, and so it just slides on through. The normal matter interacts normally, gravitationally, and so it's stuck in the center, while the two dark matter halos just pass right through each other. If you have a better explanation, I'm all ears. All right. So, how are we approaching this method with the best instruments, the best technology, and the best understanding that we have in present day, 2026? There are two instruments that I want to showcase to you that are doing exactly that. How do we illuminate more of the dark matter or dark energy or whatever field? Well, we want the best senses of what's actually out there. Let's take a gigantic volume complete sample. Let's see what all the stuff is out there without the hindrance of using a very small telescope, pointing it at a very small field of view and waiting for a very long time to detect the very, very, very faint light that's out there. Let's build instruments that can detect things very quickly, can detect very, very far away things very quickly, and have coverage enough to give us a full sky census of what's actually out there, which would give us the best data set to start picking apart and seeing if we can find any other explanation other than the existence of matter that doesn't emit light that can explain these things. One of the premier instruments that just turned on last year, named aptly, is the Vera Rubin Observatory. Now, one of the things that observatory is doing is the Legacy Survey of Space and Time. And that is taking a video, a movie of the entire sky by taking pictures of it every single night. It's doing that right now. And it's released some of those movies recently, and it is currently making the rest of the movies that it's going to show you. And so it's going to be doing a very good job of detecting things in space that happen very quickly. Asteroids, supernova, explosions, all of those things. But that's for another talk. I want to focus on that thing. That thing is a camera. Look at how big this camera is. Look at that. Look at it. That is, okay, you might be thinking, well, that's the biggest camera you've ever seen. You're correct. It's the biggest camera that exists. This is the biggest camera made by humans. It has 3,200 megapixels on its CCD, 3.2 gigapixels on its CCD. I know that you can read faster than I can talk. I'm just going to read it anyway. It would take 400 Ultra HD TV screens to display a single Rubin image. This thing is a monster. Would you like to see one of its images? Yeah. But that's not all, folks. We also have DESI, the Dark Energy Spectroscopic Instrument. Now, if you want to ask me about dark energy, go ahead. Fuck if I know. But this thing also is a gigantic survey instrument where it is making one of the largest catalogs of galaxy detections and one of the deepest reaching catalogs, meaning it's detecting galaxies at farther distances that we have ever seen before, in an effort to make the most populated, deep, complete map of galaxies in our observable universe. And it, like the Vera Rubin Observatory, is still taking data, but they just, either earlier this year or last year, released one of their first results. Would you like to see one of them? Yes. Okay. Here's a map of the Milky Way. Here is the Milky Way's disk. Here's the galactic center. These two little guys are the Large Magellanic Cloud and the Small Magellanic Cloud, some dwarf galaxies that are orbiting around us. The DESI instrument is going to label for you its fields of view. Every single one of these circles is a spot that they looked at on the sky and detected as many galaxies as it could observe. Keep on filling this in. Keep on filling this in. You know what? Let's just take a panorama. Let's just look around here. Let's just look around. Thank you. And why don't we just zoom in on one of these wedges of the sky that DESI has looked at? All of these images are galaxies. This is real data. Let's go. Every single speck of light is a galaxy! And this is real! These are real observations! Even me, this is my career. I'm like, that's nonsense! At least astronomers spend your taxpayer money well. So after all this, after all of these studies, including these, what are our top candidates for whatever the hell dark matter is made of? Is it there? Why is it there? Who is it? There are two top candidates for what dark matter could possibly be constructed of. WIMPs, weakly interacting massive particles. And so these would be new subatomic particles that we have never detected before, that have more mass than traditional particles that you know of, protons, electrons, neutrons, that would not interact with photons, would barely interact with stuff like protons and electrons and neutrons, but it can interact with itself. If a WIMP and a WIMP come together, they can interact with themselves, but they don't interact with anything else, which matches how we model dark matter nowadays. We don't know what it's made of, but we model it with mass, and the way that we model it is like a fluid that if two particles of dark matter in our simulations come into contact, they just go right through each other. They don't interact with one another, and when we do that, we produce realistic galaxies in our simulations. So this would sort of track with what we are modeling it with now, with very little information about what it's actually made of. The other top candidate is MACHOs. Massive compact halo objects. Massive, very, very, very dense halo, meaning that if you imagine a spiral galaxy and it's a disk, it's surrounded by a roughly spherical distribution of stars, and we call that part of its structure the halo. And so if dark matter exists, then we're saying if it's MACHOs, then there are very small, not very bright, very, very dense compact objects that populate the halo, as well as old stars. What could these possibly be? Neutron stars, which is the condensed core left over from a star more massive than the sun, or what we call intermediate mass black holes, meaning that we've detected black holes, we know the existence of black holes, we've studied black holes that have a mass similar to that of the sun, and so they're about the size of a small star to the size of a planet, or supermassive black holes, which is what me and Madeline study, where we've detected those at the centers of galaxies that have millions or billions of times the mass of the sun, and they're about the size of a solar system. We've detected both of those, hundreds, thousands of those. There should be something in the middle, something that's more massive than a star, but less massive than something that's a million times the size of the sun, but we have not yet agreed that we have detected one. There have been people that have reported that they have detected one, They didn't, but that doesn't stop them from reporting that they did. So we don't know. We don't know. And if it's neutron stars, good luck finding those, because those things are as big as about a city, and so they're very hard to see. They don't emit a lot of light, so it could be that, but I don't know. I don't know. There has been a little bit of work done for machos. There has been more recent work done for WIMPs, and that was most of the reason why I wanted to talk to you tonight. So, for WIMPs, we looked to our particle physicists, the same particle physicists that construct CERN and S-Phoenix and all the big particle colliders that are in America and in Europe, under Switzerland, I'm pretty sure. We have some professors at Georgia State University that have their students build pieces of colliders, super colliders, that then are taken and used in the construction of these big things that have made some of the most groundbreaking discoveries in physics, like the detection of the Higgs boson. If you read about that a couple of years ago, they have said, okay, well, if this is a WIMP, then there has to be some physical properties associated with it. For example, it's going to be larger and more massive than stuff like protons. So let's generate a little WIMP here. Allegedly. Come on, there we go. I see it moving. It's a WIMP. Okay. If this is a WIMP, it's not going to interact with stuff like photons, which are particles of light, which pass right on by it. It's not going to interact with protons, and you can see the proton is smaller because the WIMPs are more massive. But if it comes into contact with another WIMP, our standard, the standard model of particle physics says that if they interact with one another, if we're correct about their chemical makeup, then these things will emit gamma rays when they interact with each other, and a couple of other subatomic particles. What are gamma rays? There's the Hulk, but also it's the most energetic form of light that we can detect, and we've detected a lot of it. We've detected gamma rays. X-rays is what I just showed you. They're ranked number 2 in energy. So how do you prove or find evidence to support the existence of WIMPs? Well, we can't see WIMPs, but if they do emit gamma rays, then let's look and see if we can detect the gamma rays. This is an all-sky map of the Milky Way measured by the Fermi Gamma Ray Telescope, which is one of our premier telescopes in space, and its only job is to flail out its wings and say, I've detected a gamma ray or I've not detected a gamma ray. You can't focus those. You can't use lenses. Gamma rays are too powerful, so either you detect one or you don't. And this right here, all of the yellow is the most amount of gamma rays that we detect. This is the disk of the Milky Way. This is towards the Milky Way center. This is behind us in one way. This is behind us in another way. And you see all this gamma ray emission coming from the center of a galaxy. Those are sometimes referred to as Fermi bubbles, because our supermassive black hole used to be eating a bunch of stuff, and there used to be jets coming out and poking out of the top and bottom that were exerting an enormous amount of radiation up and down relative to the disk of the Milky Way. And so there's still remnants of that, even though our black hole isn't really eating anything anymore. So somebody took 20 years worth of observations with the Fermi Gamma Ray Telescope, and what this author did, that just published something last year, Totani et al. 2025, this map right here is of the center of the Milky Way. Like the very center. This is to the left, this is to the right, this is above the disk of the Milky Way, this is below the disk of the Milky Way. There's a lot of gamma ray sources that are in the disk, like supernova remnants and big old shock waves caused by stars blowing up that are hitting really cold gas, and so they just block that all entirely, just block the Milky Way. All of this stuff, everything that you see in yellow and orange, represents gamma ray emission that has been detected. This is real data. And this fellow spent a lot of time modeling and removing every single source of gamma ray radiation that we knew to exist. That includes the Fermi bubbles, that includes supernova remnants, that includes cosmic rays. Everything that has ever been cataloged that has emitted gamma rays and now we've detected has been removed from the image that you are seeing. And so if that was all, if that was a complete census of gamma ray radiation, you would see nothing in this plot. That is not what we see. We still see gamma rays, even though we have accounted for every single known source of gamma rays. And he said, okay, if there's still stuff there and we don't know what's causing it, let's see if the gamma rays produced by WIMP annihilations, let's see if it matches the type of emission from gamma rays that we see, which is what this plot shows you here. You should look at this like a spectrum, where you have the amount of photons detected on the y-axis, which is another way of saying intensity. And then on the x-axis, you have wavelength, or you have energy as part of the same thing. So in the gamma ray regime, these are referred to as low energy gamma rays, and these are high energy gamma rays. The data points here, these circles with the error bars, those are actual measurements of what's going on in the center of the Milky Way. Those are independent and do not care about our explanations as to why it's happening. That is observed, that is real, it is there, regardless of what our explanation is. Those open circle points. Each of these curves, the green curve, the red curve, the blue curve, represents the kind of gamma ray emission that would be caused by 3 different kinds of WIMP-WIMP interactions. The red one is a WIMP-WIMP interaction that annihilates and produces a couple of quarks, which if you break a proton apart, you'll find quarks. They're more subatomic they're more fundamental than protons. You can have a different kind of interaction where they'll still annihilate each other and you'll get bosons, which are the particles that do the job of communicating forces between different things. And then the green one is you'll get a couple of leptons, which are like electrons. So regardless of what's going on, these 3 curves represent theoretical WIMPs that annihilated each other, turned into some subatomic gobbledygook, and then emitted gamma rays after they decayed. You ever heard of radioactive decay, where some neutron will turn into a proton and emit a lot of radiation or whatever? That's the same thing that's happening here. And the whole point of this is that 2 out of the 3 curves in this theoretical gamma ray emission from WIMP-WIMP interactions seems to agree pretty well. It doesn't match, but it seems to agree pretty well with the gamma ray emission that we observed. So the take-home point is, we observe gamma ray emission that is unexplained currently by anything that we have observed to emit gamma rays. When we compare that to the theoretical prediction of gamma rays produced by WIMPs, annihilating WIMPs, it seems to be a more close match than not a close match. So is it WIMPs? I don't know. Is it machos? I'm a black hole scientist, so I want it to be black holes, but it's probably not black holes. I don't know. More to come, but for the skeptics in the audience, I couldn't help but include a couple of memes in here. We thought the ether was a real thing in the 80s. We think dark matter is a thing in the 10s and 20s. We're searching for shit that might not exist. I don't know. When we can't explain something, why is it always dark matter, exotic matter, or dark energy? I don't know. Look how beige that picture is. That's one of the beigest movies I've ever seen. The whole color palette is just beige. And then, you might know this guy if you've seen any of the sci-fi, channel or sometimes the History Channel, Michio Kaku. No, it's not dark matter. It's gravity leaking from a parallel dimension. You're not helping. I do wish that I have as good of hair as you when I am that age. And also my personal favorite, they all ask, what is dark matter and where is dark matter? But nobody asks, how is dark matter? And contemplate that while I say thank you so much for coming, everybody. A shameless plug, we do things at the Fernbank Science Center, and we will have a talk about open clusters, big clusters like the Pleiades that exist, that consist of big, bright and blue stars, and there has been very, very, very high precision measurements on how to determine their ages given by a PhD candidate in our astrophysics department at GSU. That is happening at Fernbank. That is happening next month. If you want to know where Astronomy on Tap will be at any time, scan those QR codes up there. And also, last announcement, Astronomy on Tap, you guys have been generously coming to us for so long that we will, the next time, I hope, have merch. We will have merch. We will have t-shirts, we will have pint glasses, we will have lapel pins, and we will have a raffle every time that we are here, and you will have an opportunity to win a free t-shirt or a free pint glass. So please be sure to follow us on Instagram or on our website to know when we are coming back. So thank you so much again. I will take any questions anybody has.
I've run the mic for you. Questions. I'm running the mic. Raise your hands. Raise them high. I don't know about y'all, but I definitely learned something. You didn't learn something, you should have been entertained to say.
Yeah, that's always what I hope.
I was wondering, so you said that, well, first, thank you for the talk. It was wonderful.
Thanks.
But I was wondering, you said that the gamma radiation emitted from a WIMP-WIMP interaction produced, and all of those produce a similar curve to what you observe. I was wondering like how those the movement just seems so theoretical to me. How you calculated the type of gamma radiation and like how that matched with a real observation.
Oh man.
I wish we had a particle physicist.
Yeah, I know. I wish I had more beer before I answered this one. Let me answer it this way. Nothing that we have observed or that we know to happen. We know supernovas happen. We know hypernovas happen, which are more powerful versions of supernovas. We know what happens if an extremely powerful shock wave runs into one of the coldest things that we know, which also produces gamma rays. None of those situations that we know to exist produces gamma rays at the extreme energy distributions that were on that plot. And so even if we're not right, we don't have something that explains that high energy gamma rays, and so what the hell could it be? How we model it is a lot of quantum mechanics, where in the standard model of cosmology, which includes particle physics all the way up to quantum mechanics, general relativity, all of the best theories that have predicted the most things the most accurately in present day 2026, they have rules about what kinds of particles can exist, and if a particle exists, and if it has this sort of mass, which we dictate, we say that if these things exist, they have to have this range of masses that limits the other properties that these particles can have, including what their internal makeup is, whether or very specific things about the internal magnetic fields that make up all of these small particles. And if we're right about all of that, which means if we're right about how all other particles exist, which particle physicists tell me that they are very confident in that, I don't know, but all of those rules dictate what kind of emission happens when a pocket of subatomic particles, like what we think makes up WIMPs, hits another one. And if I go any more in depth, I'm going to have to describe, quantum chromodynamics, and I really, really want you to enjoy this night rather than not. Is that getting close enough to what you were trying to ask? Okay. And of course, that was the first question. I invited it.
My question, a little embarrassed about because I just saw like this headline on the socials.
Yeah.
It's kind of a two-parter. So recently saw where it was saying that darkness is moving faster than light. Is that dark? Like I didn't click or anything.
Sure.
Is that dark matter? And the second part of that question, I know we don't know what dark matter is or what it's made of. Do we know what it's doing?
Oh, very good questions. Very good questions. Is dark moving faster than light? That sounds to me like a salacious journal title that was designed to get a lot of clicks. If I'm being generous, they might have been talking about dark energy, which we know less about dark energy than we do about dark matter. But we know that the universe is expanding. In fact, we've measured it very precisely with some of the best instruments that we have available. Everything has told us that the universe is expanding. When we say that, we mean that the total volume of the universe is increasing with time. So imagine that you were standing right there, and then I was on one of those really, really short, useless moving sidewalks in the airport, right? Where I wouldn't be doing anything and you wouldn't be doing anything. But if I was looking at you and the sidewalk was moving backwards, then I would be moving away from you without having to walk because the sidewalk underneath me is doing the movement. The literal space-time between galaxies is increasing in length as time goes on. So if you want to refer to that as dark, then sure, the universe is expanding to the point where if you measured its expansion rate out to the furthest extents, then it would exceed the speed of light. But the speed of light is only a speed limit for things with mass, and we're talking about the universe, which doesn't have to adhere to those kinds of rules. Your second question, what is dark matter doing? Dark matter is our band-aid to explain why galaxies are rotating in the way that we observe them to be rotating. And also it's our band-aid to explain why we detect gravitational lenses everywhere, except we don't find, in all the ways that we know how to detect it, mass that's enough to generate those gravitational lenses. Dark matter is a band-aid. It's, if we're correct about gravity, mass needs to be there, and we just pile all of the mass that we can't detect into this umbrella term that we call dark matter. So what is it doing? It's explaining why galaxies be doing it. That's it. That's my best explanation as to how that works. Yeah.
We're very scientific here.
Yeah. I love hearing snorting. It's amazing.
So I don't know. It might kind of piggyback on yours a little bit, but it's called dark matter not because we can't physically see it, but because it interacts in the way that we can see.
Both.
Okay.
Yeah.
So it's not about a visual thing, but it's basically it doesn't interact with the electromagnetic spectrum, right? But
Yes.
So two things like weakly interacting. We said they are interacting with each other and then are producing gamma rays, which are on that spectrum, right?
Right.
So can you explain that?
Yes.
Bit, please? Thank you.
Really good question. We attribute all of this mass that needs to be there to dark matter because in further away galaxies, we either we will never detect photons coming from this mass, or it doesn't emit photons, period. And when those two WIMPs interacted with each other, they produce a lot of other subatomic particles, more than they do electromagnetic radiation. So if we're right in that WIMP annihilations would produce light, it is a byproduct of a much larger interaction that produced other particles of mass rather than light. So the reason why this study was focused on the Milky Way is because we are close enough to see the glimmer of the gamma ray radiation that may have come from WIMPs, may have not. We haven't proven it yet. But in farther away galaxies, that is far too dim for us to detect with our current telescopes at the positions that they are with the sizes of the mirrors that we currently have.
It's like a secondary effect.
Yeah, yes. Fantastic question.
I think there was also, do you have a question? We have one over here first, one coming to you in the red shirt over there.
I got here a little bit late, so it could be a dumb question.
Sure.
But if dark matter is the space that we see above us, is it not also all around us?
What is above in space? There is no up, there is no up, there is no down. You are correct. If we are right about the distribution of dark matter, then it is surrounding almost every major galaxy in the universe like a cocoon, where in the center of this gigantic spherical shell of dark matter rests galaxies that we have traditionally detected by taking pictures of them. It is, besides the bullet cluster, we have not, to any scientist worth their salt, there's some studies that I don't believe you. There are dark matter halos that are roughly symmetrical shells around major galaxies. And so it's completely enveloping as opposed to having a preferential concentration in some region of a galaxy. Yeah.
So dark matter is like not this area that we're really at.
Correct. Yeah.
I am pulling for the Winston, the machos.
All right.
Finally, is there anything that we know in science? We've discovered how the undetectable is detected that could apply to this problem.
Ooh, okay. That's a really good question. Yes, that's a really good question. Yes. Is there anything that we know in current science that will make the previously undetectable detectable that applies to this specific problem? Making the undetectable eventually detectable is the success story of the best theories that we have of physics. So to give you a quick story, Einstein wrote down the general theory of relativity that described gravity as a byproduct of curvatures of space-time rather than a force. He did that in the early 1910s. He also predicted the existence of black holes, which nobody believed until the late 90s, early 2000s. And really that was only a few people, and then in the mid 2000s, everybody started believing it, right? Because Hubble started detecting them. It's a black hole detection machine. He also detected the existence of gravitational waves, where if space-time is a fabric that can be warped, and you exert a large amount of gravitational energy into that fabric, then you should get ripples in that fabric in the same way that you do any sort of fluid. And he said, we should be able to detect that, but it's probably too weak that we'll never detect it. He wrote that down in let's just simplify, 1910. I can't remember the exact year. A couple billion years ago, two black holes that were orbiting each other eventually collided, merged, and in that process released an enormous amount of gravitational potential energy that rippled out as gravitational waves. That happened billions of years ago. And those gravitational waves travel at the speed of light. And so those things were traveling to us from a couple billion light years away, which means it takes a couple billion years for them to get here. Fast forward to 65 million years ago. These gravitational waves are still emanating out in all directions, some of which are towards the Milky Way. 65 million years ago, dinosaurs were walking the Earth, right? Fast forward to a couple thousand years BC. We've got ancient Egyptian astronomers trying to draw shapes of things that look like a bear, in space, whatever the hell. Then fast forward to 1910, 100 years before we detected gravitational waves, and Einstein writes down the equations that would later predict in 100 years our first detection of gravitational waves in 2017 with the LIGO instrument. So that is our complete story and why we adhere to the predictions from these theories, because they predicted things that no one thought would have been predicted. So now we're at this point where we have the best theories that we've ever had, and we've reached this new thing where we do not have the language capable of describing what is happening. And so you have these experiments where you have theoretical WIMP-WIMP annihilations, you have theoretical models and simulations that use larger particles to represent dark matter distributions, that use smaller ones, that use fluid dynamics, that use whatever. All of them are making predictions. The one that we will always talk about, like I'm talking about with the theory of relativity, that's going to happen after one of these things makes the most correct prediction. And then after that, we're going to put that one on the same pedestal that we do general relativity and quantum mechanics. So right now, I don't know. I hope that I'm alive when we figure it out, though. Yeah. Is that a good enough answer? Okay.
So I have a couple of questions as well. With both WIMPs and machos, there seems to be this emphasis on them being like massive particles. I don't understand why it's so crucial that we think of these non-interacting but super mysterious particles to essentially be massive. Why not minuscule? Because I just feel like that's almost like a theoretical.
Yeah.
Sure.
Great question.
The other question is, like from what I understand, black holes are also kind of like these massive cosmic objects that are just swallowing everything. And it wasn't until a couple of years ago that scientists from, okay, so they were able to like detect these things, and like they were able to see like the actual. We got a picture of the black hole itself. So if a black hole is also just kind of swallowing everything that comes its way, and yet we are able to detect them.
Yeah.
How is dark matter in any way different, that we're not able to do the same thing by pursuing that line of technology that we're using to detect black holes themselves?
What a great set of questions. Yeah. Okay, this is going to be our last question because that was so good. Your first question, why do they have to be massive particles? It's because if the theory of relativity is correct, in that our estimates of the amount of mass needed to produce the lenses that we observe is correct, assuming that's all correct, you need so much mass. You need so much mass. And if you tell me that it's particles, those things are so much smaller compared to large scale things like stars, like supermassive black holes, like whatever. So it naturally dictates that if it's particles, they have to have a huge mass. They have to. Otherwise, there's no amount of subatomic particles that you can surround a galaxy with that would realistically create a galaxy in a simulation, other than enormously massive particles, more massive than the particles that we know to exist. Your other question, and I'm copying this from my advisor, Dr. Misty Bentz, who is a black hole expert, worldwide expert. Black holes don't suck. They don't. They are not cosmic vacuum cleaners. They are not gigantic holes in space that are sucking in everything. Black holes are simply gravity. That's all it is. If I replaced the sun with a black hole of the same mass, and I asked you if there was any dynamical changes to the solar system at all, the answer would be no. It would get cold, it would get dark, but nothing would change, because if it's the same mass, then it is the exact same gravitational pull that's being exerted on everything else. And so black holes are simply gravity on steroids. It's a gravity laboratory, because all of the effects of gravity that we understand that are caused by anything from a proton to a supermassive black hole behave in the exact same way according to the theory of relativity. So we're able to target black holes because it's a concentrated mass that we have predicted to be at the centers of galaxies, and we knew that they had to be surrounded by light in order to take some sort of a picture, right? We took a picture of the accretion disk, not of the black hole. For dark matter, if we're right about it, then it's either very small particles that are dispersed over size scales of a galaxy that are bigger than anything that we have detected with light, or they're neutron stars or black holes that adhere to the same thing, where they're so spread out over such a large volume that there isn't a technique or an instrument like the Event Horizon Telescope that we could use to probe that kind of distribution. Does that make sense?
Yes.
And with that, we will turn the World Cup back on, and I will thank you all once again. Thank you.